Good day, you're welcome to Enzyme Kinetics, where we try to simplify some of the processes, some of the equations and derivative in enzymology. So today I'm going to be looking at enzyme kinetics. Now, what is kinetics? The study of the reaction rate and how they change in response to changes in experimental parameters is known as kinetics. So when you begin to consider the rate of reactions and how this changes, when you perform an experiment on the rate, okay, we are talking about kinetics. Now, kinetics is the study of the rate of reaction. When you talk about the velocities, that is kinetics. Now, why do we study enzyme kinetics? We study enzyme kinetics for obvious reasons, and some of those reasons increase: one, to measure the concentration of enzyme in a mixture by looking at its catalytic activity; to measure the purity of an enzyme by measuring its specific activity; to measure its catalytic efficiency and or specific of for different substrates. We measure the reason why we do kinetics is also to compare different forms of the same enzyme in different tissues or in different organisms, so that we can know how the enzymes perform in different species. Now, we study kinetics to measure the effect of inhibitors, which can give us information about the catalytic mechanism, the structure of active sites, and the potential therapeutic agents. We also study kinetics, to measure the dependency of velocity on substrates, so described by many forms of enzyme using that Michaelis-Menten's equation. Okay. Now, looking at the kinetic parameters when we talk about enzyme, we talk about the Kn, which is the Michaelis constant. We talk about the Vmax, which is the maximum velocity. We talk about the Km, which is the turnover number, which relates Vmax, the maximum velocity, to the total enzyme concentration or the total active site concentration. We also look at the kinetics, such as the ratio between the Kcat and the Kn, and this is known as the catalytic efficiency of an enzyme. Now, the catalytic parameters can be determined graphically by measuring the velocities of an enzyme catalyzed reaction at different substrate concentrations. Now, we are going to look at some of these derivatives, how Michaelis-Menten's equation is being derived, and we are going to be using some assumptions. So first of all, there are two assumptions that are normally used: the rapid equilibrium assumption and the steady state assumption. So first, we are going to be looking at the rapid equilibrium assumption. Now, a rapid equilibrium assumption, which could be described as a pre-steady state in which the enzyme is assumed to establish a rapid equilibrium between the reactants E and S and the product ES, where E is the enzyme concentration. Rather, we can call it free enzyme concentration. S is the substrate concentration, and also ES is the concentration of the enzyme substrate complex. Now, these assumptions we are talking about include: one, that at the pre-steady state, okay, that products are equivalent to zero. This means that at the rapid equilibrium, the concentration of products formed is very negligible. It might be assumed to be 0. So in other words, we are just saying products are not yet formed. In as much as this assumption might not be really correct, to say that once the sum of these enzyme reactions, enzyme catalytic reactions could occur milliseconds before once the reaction starts. But this is an assumption we are making, that at this pre-steady state we don't have product. Number 2, we also assume that the substrate is far greater than the enzyme. This means that the concentration of the substrate overwhelms the enzyme, that the formation of ES will be assumed to be negligible when compared to S. And also for the fact that ES breaks down to enzyme and substrate. So when you compare the substrate in terms of the enzyme, the substrate overwhelms, it's so large. Now, number 3 assumption is that the total substrate is just equal to the substrate concentration. The reason being that since in our point 2, where the substrate overwhelms the enzyme, the formation of ES does not actually affect the total enzyme because it is quite negligible. So we don't talk about total substrate, we just talk about substrate concentration. And finally, we also assume, or rather it is true, that the total enzyme remains the free enzymes plus the bound enzyme, where ES is a bound enzyme, the ES complex is bound. So where ET is the total enzyme concentration, E is the free enzyme concentration, and ES is the bound enzyme concentration. Okay, so you follow me, let's get on. Now, considering this reaction, because that is what we had just established in a rapid equilibrium, that E plus S forms ES. Okay, the forward reaction has a rate of K1, while the backward reaction is K2. Now, because products are not formed, we don't expect ES to break down to products. Now, let's look at the rate of forward reaction, which is K1 multiplying E and S. Now, the rate of backward reaction is K2 multiplying ES. Now, at equilibrium, we say that the forward reaction is equal to the backward reaction. So, if that is the case, it means that K1 E multiplied by S is equals to K2 ES. Now, making ES the subject of the formula, you arrive at ES being equals to K1 multiply E multiplying concentration of S divided by K2. Each time I go fast, you can always pause the video to get the point, or you can always rewind it. But equilibrium constant KD, which is the rate of backward reaction or the rate of dissociation divided by the rate of formation. In other words, you can say the rate of backward reaction divided by the rate of forward reaction. That will give you the equilibrium constant. So KD is equals to K2 over K1. Therefore, 1 over KD is equal to K1 over K2. Now, that shows us that ES, instead of having K1 over K2 multiplying ES over S, we now have it as E multiplying S divided by KD. Now, let's remember that in one of our assumptions, which is the fourth assumption, we say that E total is equals to E plus ES complex. That's the bound enzyme. So free enzyme will be equal to E total minus the bound enzyme, the total enzyme subtracted you subtract the bound enzyme from the total enzyme, you have the free enzyme. So we are going to substitute this E in the equation 3, and when we do that, we have that ES is equal to E total minus ES all multiplied by concentration of substrate. Now you divide all of them by KD. Now we say open the numerator. In other words, when you open the numerator, you're going to have ES equals to E total multiplied by substrate concentration subtracted by ES multiplied by substrate concentration. Now we multiply through by S, all divided by KD. Now when you do that, you can cross multiply. You see that KD is now multiplying the concentration of enzyme substrate complex is equal to E total multiplied by X minus ES multiplied by S. This is simple mathematics. Now we are trying to collect like terms, putting ES on one side. Okay, so you will be left with KD. You transfer the ES multiplied by S to the left hand side of the equation. It will then be plus ES multiplied by S. Okay, now you factorize the above, you will have that ES is equals to KD. So ES multiplied by KD plus substrate concentration is equals to E total multiplied by S. So making ES the subject of the formula at this point, we are left with this equation 5. Okay, now remember that the rate of reaction or the initial velocity is equals to VO, rather, which is VO is equal to K cat multiplied by ES, which is equation 6. So we have to substitute that ES in this equation, and when you do that, you have that VO is equal to K cat multiplied by total enzyme concentration multiplied by substrate concentration, all divided by KD plus substrate concentration. Now, at saturation, where all the enzyme sites are saturated, okay, at this point all the enzymes will be in the ES form. So the total enzyme at that point is equal to ES. And at this condition where all the sites are saturated, the enzyme is assumed to have attained its maximum velocity. So at that point, VO becomes Vmax. Okay? So then it means that Vmax is equal to K cat multiplying E total, because E total is equal to ES. So that will mean that when we substitute that Vmax in our equation 7, we are left with VO equals to Vmax multiplied by S all over KD multiplied by S. Now, this actually looks like the Michael-Menten equation. Then we say equation 9 could be regarded, or rather it's supposed to be in equation 8 could be regarded as the Michaelis-Menten equation based on one assumption that KD is equal to Km. Okay, that is equation 9. And when we do that, we have that VO is equal to Vmax multiplied by S all over Km plus X, and this is the Michaelis-Menten's equation. But remember, the only assumption is that KD is equal to Km, and this is only achieved at the pre-steady state, which is only in rapid state equilibrium, where we are saying that no products have been formed and there is an established relationship, which is an established equilibrium between the reactant, which is the substrate plus the enzyme, and the ES complex. We are also saying that for this to be possible, ES complex has not broken down to products. So you have derived the Michaelis-Menten's equation. Now, let's also look at the steady state assumption. How do they actually derive this particular equation? So the assumptions in the steady state says that in steady state assumption, it is assumed that the enzyme catalyzed reaction has reached a point where the concentration of ES is constant as reaction progresses. At the steady state, products are formed, but the ES complex does not change as the reactants, which is E and S, combine to form EX complex. The ES breaks down to give product and the enzyme. So what we are saying in this is that our E remains the enzyme concentration, which is free enzyme concentration. Our S is the free substrate concentration. Our ES is the concentration of the enzyme substrate complex, and then P is the product. Now, these assumptions is saying that the change of ES per time is zero, meaning that at steady state, the rate at which ES is formed or the rate change of ES is zero, which says that the rate of formation of ES is equals to the rate of its breakdown. So we also say that, and the assumption also is that the substrate is far greater than the enzyme. I have explained that. Total enzyme, total substrate is equal to total substrate concentration. Okay, because the bound the ES form is negligible, so it does not really affect the total substrate concentration. And we say that the E total is equal to the free enzyme plus the bound enzyme. That will give you the total enzyme. Now, let's look at consider the catalyzed reaction. So E plus S will give you ES. The forward reaction rate is K1, the backward reaction rate is K2. Now ES breaking down into E plus P, we talk about the K cat, which is the rate constant for the formation of the product, and this K cat can also be described as the turnover number, okay, of the enzyme. Now the rate of formation is being given and also the rate of breakdown. Now we have two values for the rate of breakdown, and these values is because ES is breaking down in two directions. When ES is breaking down in the backward direction to form E and S, and when ES is breaking down to form the products. So at steady state, we say the rate of formation of ES is equal to the rate of breakdown of ES. So we have that K1, which is the rate of formation, K1 multiplied by E and S will be equal to K2 multiplied by ES plus K cat multiplying by ES. So if you do the simple mathematics of factorizing, we have that K1 ES E plus E multiplied by S is equals to K2 plus K cat all multiplied by ES. So we make ES the subject of the formula, and we have that ES is equal to K1 E multiplied by S all over K2. Now we have to introduce sorry, there is an error somewhere. The reaction 2 is not complete because the denominator should be K2 multiplied by K cat. Okay, so please correct that error where you're writing it down. Equation 2 is K1 multiplied by enzyme concentration multiplying the substrate concentration all over K2 plus K cat. So now we say we introduce another constant which is known as the Michaelis-Menten constant, or you simply say it is the Michaelis constant. Okay, we say it is the rate of breakdown of ES, which that rate is equals to K2 plus K cat, all divided by the rate of formation of ES, which is K1. So we say that Km gives you K2 plus Kcat all over K1. Therefore, 1 over K1 will be equal to um, K1 over K2 plus Kcat. Okay, in other words, in our equation 3, we have that Es plus S all over K1, which will give you our Es complex. Okay. Now, like we said earlier, remember that the rate or the initial velocity VO is equals to Kcat multiplying Es. So we are going to substitute Es, and you're down with equation 7, where you have that VO is equals to Kcat multiplying total enzyme multiplying substrate concentration, all divided by Km plus substrate concentration. Now at saturation, we've said that before, that all the enzyme will be in the Es form because all sites are occupied. So Vmax is equals to Kcat multiplying E total at that point, which gives us the equation 8, which is VO is equal to Vmax multiplied by substrate concentration all over Km plus substrate concentration. And that is our Michaelis-Menten's equation. Now, in this equation, when you make a plot of V and against S, you're going to, um, you're going to have a plot that looks like this, which is a rectangular hyperbola. Okay. Now we are saying that the Michaelis-Menten's model to explain the hyperbolic dependency of VO on S is in an enzyme catalyzed reaction. Therefore, the chemistry occurs enzyme bind to substrate to make a non-covalent ES complex. Okay, remember that that complex called ES is not forming covalent bonds, otherwise it will not break up again. But because of the non-covalent nature of ES, the enzyme can also dissociate. Now the equation V equals to Vmax multiplied by ES divided by Km plus this means that for an enzyme acting according to the simple model which we are given before, the plot of V against S will be a rectangular hyperbola. Okay, when the enzyme exhibits this kinetic behavior, unless we find other evidences on the contrary, we assume they are acting according to the above, and they call them the Michaelis-Menten's enzyme. Okay. Now, Michaelis-Menten method obeys the first order and zero order kinetic reaction, therefore forming an asymptote, a parallel close to the x or y axis, but not touching any axis. Okay. At the start of the reaction, it was observed that VO increases as substrate concentration is increasing, following a first order kinetics. But when the active site is completely saturated, the enzyme is said to achieve a maximum velocity in which VO is no longer increasing as S is increasing, thereby achieving a zero order kinetics. So we are going to stop here, and then I expect your questions. You can send it to me as mail, you can send it through WhatsApp, or whatever way you can send it to me. Thank you very much. And for you to really understand, don't watch this as a movie. Always write down some of these things that we have seen. Thank you.